Hello, it's been a while since I've made a video on C-star algebras, but don't worry, it will come in due time. But for now I want to focus on modular arithmetic since it's come up in connection with something that I've started to become interested in later weeks, one might say. So if you have no idea what modular arithmetic is, I'm going to talk a bit about that first, and then I'm going to talk about the game engine Godot and how its implementation of modular arithmetic is a bit weird in my opinion. So let's sit back and first off figure out what is modular arithmetic if you have no idea. Otherwise you can of course skip this section. If you feel comfortable with modular arithmetic, how it works and what are congruence classes, modulo n and stuff like that, then of course just skip by this and get to the next section. So, first off, what is modular arithmetic? Well, it's simply arithmetic where we only care about remainders. So for instance, how it looks in practice is something like this. You will see a line like this where 5 plus 3 is equal to 8, and then you see these three lines stacked on top of one another, and then you see that this 8 is related to this 2, and then you see this parentheses modulo 6 like this. And what this means is simply that 8, which is equal to 2 plus 6, has the same remainder as 2 when divided by 6. And this is something, this here is something we usually call that 8 and 2 are congruent modulo 6. And more generally, P and Q are congruent modulo some number n if and only if P and Q have the same remainder when divided by n. You may see some other characterization of modular or this congruence relation in books and stuff, but I like this simplistic one the best. So now that you've seen the definition of modular arithmetic and congruence modulo n, you may wonder, why do we even do this? And to answer this, we have to answer another question first, and that is, what does it actually mean for two numbers to be congruent modulo n? And the simple answer is that it means that if we ignore multiples of n, then these numbers are really the same thing. And this becomes very useful when we deal with some kind of cycle. So, for instance, if we have the time of day, that is a typical cyclic event. For instance, if I ask you, what time is it? I'm not asking what time of what day of what year, but I'm only asking what time of the day is it normally. So say that the time is 10 o'clock one day, and then we let 25 hours pass, then the time is of course 11 o'clock. Because adding 25 hours to the time of day is basically the same as adding 1 hour to the time of day. Because we're working on a cycle of 24 hours. So we're working in modulo 24. And 25 is congruent to 1 modulo 24. So the reason why modular arithmetics are so useful for human beings especially is that they can often turn problems of big numbers into problems of small numbers. And as an example, I'm going to do the following calculations here that you see: 131 and 952. These are moderately large numbers, nothing special, but they can be dealt with using modular arithmetic very easily. So say that we're working in modulo 5 and we want to realize, okay, what is 131 plus 952 congruent to modulo 5? Well, then we can, of course, calculate 131 plus 952, brute force that, and then we can see how many times we can subtract 5, and then whatever we have left must be the remainder. But we can do it in a much more elegant way, and that is by realizing that 131, well, that's of course 1 plus 130, and 950 is of course 950 plus 2. And then we note that 130 and 950, these are both divisible by 5. And therefore, in the world of modulo 5, 130 and 950 are 0. And that is the key realization, because then when we deal with modular arithmetics, then 130 and 950 can be disregarded completely. So this large sum that we began with can be turned into this small sum, because 131 plus 952 is congruent to 1 plus 2, which is equal to 3 modulo 5. And likewise, we can do the same with multiplication actually. It works just the same. 131 times 952, well, we subdivide them. 131 is of course 130 plus 1, and 952 is 950 plus 2, just like before. And 130 is just the same as 0 modulo 5, and 950 is the same as 0 modulo 5. So these can be ignored, and we're left with 1 times 2, which is equal to 2 modulo 5. So while the first line here can be calculated by hand pretty easily, even if we have 131 and 952, this other line can be kind of tricky to do by hand. Or at least if you don't have a pen and paper, this can be difficult to figure out the remainder modulo 5 unless you use modular arithmetics like I did here. And I want to note that this works specifically because 130 and 950 are congruent to 0 modulo 5. Otherwise, we couldn't just ignore them. Otherwise, we would have had to replace them with the remainders modulo 5. But when we have that they are congruent to 0 modulo 5, they are basically the same as 0 when we don't care about multiples of 5. And this trick that I used here in these calculations up here, this works for general numbers as well. So if we denote by x mod n the remainder when dividing x by n, then a plus b, when we want to calculate the remainder when we divide by n of this sum, we can of course subdivide it like this, just like I did up here. So a mod n, I took this number here, became this, and then b mod n, 950 plus 2, became 2, like this. And the same works for products as well. So a mod n, 130 plus 1 becomes 1, and b here, which becomes b mod n. So we see here 950 plus 2 becomes 2 mod 5. And this always works, and this is why modular arithmetics are so useful when dealing with problems of cycles and stuff like that. We can simply reduce everything down to very small numbers very quickly. And one last point I want to talk about when it comes to different numbers when we work in modulo n. So when we deal with regular numbers, then there is an infinite amount of numbers. But when we work modulo n, then there aren't that many options. In fact, there are only these possible remainders. If we have any number, any integer really, then the remainder when dividing that number by n is one of these options. You cannot have any other remainder. And this is something that comes up every time. No matter what integer you have, it is congruent to exactly one of these numbers up here. And that is something that comes up all the time, all over mathematics. And for instance, every number is congruent to either 0, 1, or 2 modulo 3. And we can also talk about even and odd numbers as being congruent to 0 or 1 modulo 2. So really, these things come up all over the place. And generally, we can call these numbers 0 to n minus 1 the congruence classes modulo n. And this is an important concept, the congruence classes modulo n, because that is really what modular arithmetics is about. Modular arithmetics can be seen as basically the same as finding the correct congruence class for a specific number modulo n. So say that I have 76, and then I want to figure out what congruence class is it modulo 5. Okay, now that 5 is extremely ugly. So let's write it again. Then we have 4 options. Either 0, 1, 2, 3, or 4. No other remainder can come out of this expression here. And then, of course, since 76 is 75 plus 1, this is, of course, equal to that number in here. And this is normally how we do modular arithmetics. We find the correct congruence class in our specific problem. And with that, I would like to go over to the game engine Godot and how it implements modular arithmetics. Here you can see a sample project that I've been working on to familiarize myself with the game engine that is Godot. And as you can see here, as any good game, it has a menu. So for instance, we can resume gameplay, we can restart, and we can quit the game. And we navigate between these options by using our keyboard. So pressing up, we go up, and pressing down, we go down. But what happens at the edge? So say I press down here when I'm at quit. Then I turn up to resume. And then I go down, and then I cycle. So I cycle like this. And the same when I press up. And what happens now? I get down to quit, and I cycle the same way here. So really, when I implement this in code, I need to use modular arithmetics. So let's just be very clear what I'm doing. I'm going to change the code and restart so that you can see what's going on more clearly. So now you can see that I've relabeled my menu here. So we have 0, 1, and 2. So really what happens when I navigate between these options, I'm just navigating between congruence classes modulo 3. So when I'm at 0 and I go down, then I add 1 to the congruence class and I get to 1. Then I add 1 more to the congruence class, I get 2. And then I add 1 more to 2. And then I get 3, of course, the congruence class is 3. But 3 is the same as 0 modulo 2, so then I get back to 0. And the same if I go the other way. So if I go from 1 to 0, then I subtract 1, and then I get to the class 0, and then I subtract 1 again. But 0 minus 1 is the same as 2 modulo 3, because minus 1 is equal to minus 3 plus 2, and minus 3 is divisible by 0, or divisible by 3, sorry. So really, what I'm doing is I navigate between congruence classes here modulo 3. But then how do we implement this in code? Let's see, by going over to the actual script view. Okay, so here is the code for handling the menu and how to switch between menu options using the user interface. So here we have, you see, if input action is down, then we add 1 to the selected menu. So if we're at option 0, then we went to 1, and then we check, okay, what congruence class is it, modulo 3, and then we change the menu accordingly. And we can just do this by cycling downwards, and since the layout of my options were 0, 1, 2 in descending order like that, when I go down, I want to add 1 to what selected menu is. So selected menu here is simply the variable that keeps track of which congruence class we're in right now, or which menu option we should have right now. So it simply cycles between congruence classes. And since we're going down to increase the then we increase the congruence class, so then we take and add 1, and then we figure out the congruence class like this using the modulo operator. So when we're coding, we use this percentage symbol right here. But what should we do if we go in the other direction? So say that we want to implement this for the up direction instead. Then of course, since up is the opposite of going down, then we would like to just have this to get the correct congruence class. But this doesn't actually work. And let's see why. As you can see, the game screen looks the exact same as before. And if we go and press down, everything works just fine as intended. But let's see what happens when we press up. Works fine. Works fine. What happened? Let's press up and then we get back at 0. Okay, so what is going on? This thing is not doing what it's supposed to do. It cannot find the correct congruence class. And why is that? Well, let me tell you why by going back into the code. So now we're back in code, and the problem really when we use this particular way of writing the code in Godot is that Godot does not process modular arithmetics the way I described it earlier by saying this basically is a number modulo 3 and how we were supposed to find the correct congruence class. But Godot doesn't really do that. Instead, what Godot does, it can have a negative number here. It can have a negative remainders. It just cares, okay, if you have a number that is divisible by 3, okay, if it's slightly smaller than 3 or slightly smaller than 0, then we can take -1 modulo 3 or -2 modulo 3. But really, this makes absolutely no sense. Because really, as I said, modular arithmetics is about finding the correct congruence classes modulo some number, in this case 3. So why, when we take and use the modular arithmetics, do we not get that? Instead, now what happens is that when selected menu is 0, then this becomes 0 minus 1 modulo 3, and Godot actually interprets this as -1 instead of 2, which is completely insane. I have no explanation for why that is. But there is actually a way to fix this. And this is how we do it. So this is what should work. But now we're going to use the power of modular arithmetics to fix what Godot should have fixed to begin with. You remember when I said that if we add 3, that's the same as adding nothing, because 3 is 0 modulo 3. So what we can do to fix this particular problem here is to have a very elegant solution by adding 3. So really, the slightly paradoxical line of code that we have here actually fixes our problem in a very elegant manner. So let's just save that and see what happens when we run the application this time. Now we're back where we started. If we go up and down, it doesn't matter like this, but when we press up when we're at 0, we get back to 2, just like we wanted. And if you think about it, it makes sense that if you want to go up 1, you add 2 modulo 3, because adding 2 modulo 3 is the same as subtracting 1 modulo 3. So really we can actually get around this slight issue with Godot implementation of modular arithmetics by doing this. But really, this is something that shouldn't have to happen to begin, or this is not something that should have to be a problem to begin with. And let me tell you why that is. Really quickly, actually. And that is because this game project that I'm working on right here to familiarize myself with the Godot engine is actually not a project that I was working on myself. This is actually a project that I found on an online tutorial. And let me just briefly show that tutorial for you. So this is actually the blog where I found this tutorial to begin with. And it's actually something that a guy called David Pesce has done. And I have to say, this tutorial is a very good tutorial when it comes to learning the basics of the Godot engine and how it works. But it is a problem that when he implements this, and when he tries to find the solution for this problem with modular arithmetics, he doesn't find my solution. In fact, he thinks it's necessary to use this if statement here. And let me just zoom in a bit, like this, so you can actually see what's going on. So he uses an if statement instead that he basically hard codes in, because the modular arithmetics in Godot is not properly implemented. Now, of course, I managed to fix this because I know about modular arithmetics. I'm a PhD student in mathematics, and I'm used to doing these calculations and thinking about this problem. But for people who may not have the same expertise as I, even if they're good at programming and making games, and generally they know what they're doing, they can still not find the correct solution to this kind of problem because of poor implementation of its core function in the development or in the engine they're using, or the development environment they're using to code. And that's a real shame, because it shouldn't take this much mental effort to implement such a simple thing as that menu that I just showed. It should basically just be the completely intuitive code that I tried to get working first, but failed. And that is why I think that Godot implementation of modular arithmetics is flawed. Now, I haven't checked every programming language, and I don't know how other languages do in this regard. But if they do it in this wrong way, according to me, where they have negative numbers, I cannot for the life of me figure out why. Literally no reason to have such an implementation as far as I can tell. Because when you do modular arithmetics, what you want to find is the correct congruence class. You're not interested in negative congruence classes because they can be converted to positive ones. You want the remainder in positive terms. You don't want a negative remainder, because what is that even? So anyway, I guess that's it for me. Remember, when you have Godot and you want to implement modular arithmetics, if you run into issues when subtracting, you can always fix it if you apply modular arithmetics and if you take some care to figure out what's going on. And I also want to congratulate David Pesce on making an excellent tutorial series. So generally, if you are interested in making games and you want to use the Godot engine, and I don't see why you wouldn't want to use that one actually, then this tutorial is a very good first step to learning how to use the engine effectively, because basically in this series he goes over many different core components of basically any game you can think of, and learning how to do these things by someone who knows what they're doing is very valuable. Now sometimes, of course, David uses some simplistic solutions that may not be the proper ones if we think in a very crass way of how is the optimal way of implementing a solution to a programming problem. But often he mentions that in the end of each tutorial session, that now this solution that we have to this kind of problem right now, it is kind of basic, and in a professional environment you might want to do something else, but for now we're doing this just to keep things simple. So he's very good at that, and I think his explanations for the things he does is very good in general as well. So if you're into Godot and you want to learn more about the engine and you don't know where to start, I would recommend this particular tutorial here. And I guess that's it for me. So until next time, I promise I will get back to C-star algebra soon. I just needed to record this video and get this out of my system as well. So goodbye.